Hello, we are Yıldız Rover team from Yıldız Technical University. Proudly present our 5th generation rover, OASIS.
OASIS follows a multidisciplinary structure with 35 members across 7 sub-teams, 4 being technical and 3 being business, all coordinated through centralized leadership and continuous communication.
Our rover's mobility system was redesigned to maximize maneuverability and terrain adaptability. Independent suspension at each wheel improves terrain compliance, reduces vibration, and maintains stability during sensitive operations. Lightweight spooked wheels and custom airless tires enhance traction while providing passive shock absorption on rocky and sandy terrain. A dual motor hub architecture enables rapid configuration for either speed-oriented traversal or torque-focused operation, prioritizing climate performance, stability, and mission reliability. Its modular chassis allows the system to be quickly reconfigured and prepared for each task.
6 series 24-volt line battery pack is the main power source for the rover. A custom power distribution board steps is down to 5 and 12 volts for the subsystems that require these voltages.
Internal communication is made with CAN bus and handled mainly by the Jason Orin. The main hub PCB maintains communication between STM32-based subsystems and Orin. This year, spare CAN lines are also utilized for reliability in the case of a communication failure. In addition, I2C, SPI, UART, and BISSC are used for mission-specific tasks.
For rover to base station communication, 2 frequency bands are utilized. 5.8 GHz band is used for high data rate transfer and video transmission, while 2.4 GHz is used for out-of-sight long-range communication.
The 6 degree of freedom manipulator was revised to improve precision, repeatability, and modular end effector integration. A wormgear at the base axis minimizes backlash and increases positional stability under load, while 2 custom-made cycloidal reducers on specific joints boosts torque and robustness. Encoders in critical joints provide closed-loop feedback for accurate motion during autonomous typing and Type-C tasks. The lead screw-driven gripper supports an interchangeable TPU fingers and mission-specific end effector stops, and arm-mounted cameras provide continuous visual feedback to the operator.
To achieve for robotic arm autonomy, we are developing and integrating our custom video-based framework as part of the system integration process. For autonomous keyboard detection and USB plugin tasks, we use a webcam-based pipeline to obtain accurate orca pose estimations. These poses are transformed into the robot frame to generate safe collision area trajectories through optimized inverse kinematics and motion planning. The resulting plans are executed with high precision, synchronized by real-time encoder feedback from all 6 axes.
Software integration developed and executed on the Jetson AGX Orin platform. GNSS data is obtained from the onboard GPS model, and the rover navigates autonomously towards predefined waypoints using extended camel filter-based fusion of GPS, IMU, and wheel odometry for accurate localization. Within our extended autonomous navigation stack, we augment standard Nav2 with a LiDAR-based hay-aware 2.5D traversability layer for safe navigation on uneven terrain. A CPU-accelerated trajectory optimization controller evaluates multiple candidate paths considering terrain slope and roughness to reduce rollover risk and generates optimal velocity commands, while high-level decisions are handled by a behavior tree architecture. An OpenCV and YOLO-based vision system processes RGB images for objects and vehicle detection, while stereo depth enables precise 3D localization. During the searching state, the rover operates autonomously using data from Z stereo cameras mounted on the upper body and beneath the chassis. The lower Z improves visibility of ground-level objects while scanning the environment. Initial testing and validation were first performed in simulation using our custom URDF model in Gazebo.
This year, the rover science and sampling system was redesigned and upgraded. The onboard camera takes panoramic and stratigraphic photos. A subsurface sample is collected using a redesigned 15 cm drill. A core catcher prevents the soil from falling back. To reduce contamination, the sample is transferred into a 2-compartment cache box while the drill is still in the soil. After the drill is taken out, the remaining soil on the auger is placed into a container and moved to the analyzer strips with the monorail system. The levels of several gases are measured to assess atmospheric suitability, and various sensors are used to evaluate soil conditions. The soil sample is put in the revolver tubes mixed with a solvent and filtered. After that, the test kits are added to cuvettes with a siren system. 3 colorimetric tests are used: sudanthrin, hidden, and methylene blue. With a custom-made UV visible spectrophotometer, soil components are detected and samples are interpreted based on observations. Rock and soil samples are analyzed with the redesigned helium reflective spectrometer. Rock and soil types are examined using a microscope, muscle color chart, and our sedimentary archive.
To conclude, our system integration is actively ongoing alongside rigorous field testing. We are continuously validating our system under conditions, and we will continue our testing and optimization non-stop until we are 2026. Thank you for your time.